Hi everyone, I am Madam Rosmaya. Welcome to my YouTube channel. So in this video, we are going to discuss on energy levels in hydrogen atoms. When an electron moves around the nucleus, the centripetal force is provided by the electrostatic force. So we can write as centripetal force equals to electrostatic force. Centripetal force is given by mv squared per r, and electrostatic force is given by E from the proton and E from the electron divided by 4 pi epsilon naught r squared. R is the distance from the distance between the two proton and electron, or radius of the orbit. And E is the charge of the electron or proton. Epsilon naught is the permittivity of free space. From the equation above, we can write as V squared equals to E squared per 4 pi epsilon naught m Rn. So this is equation 1. Okay, next we are going to relate V squared with the kinetic energy. From the equation of kinetic energy equals to half mv squared. So we substitute V squared into the equation here. So we get half E squared per, half here 2 times 4 becomes 8. So we get E squared per 8 pi epsilon naught Rn. So this is kinetic energy. Next we are going to determine the potential energy of the electron, U. So U is given by negative E times E divided by 4 pi epsilon naught R. So we get negative E squared per 4 pi epsilon naught R. So from these two, we get the total energy. Total energy is equals to kinetic energy plus potential energy. So we substitute K and U into the equation here. So we simplify this. So this term we multiplied by 2. So we get E squared minus 2 E squared become negative E squared per 8 pi epsilon naught R. Okay, so this is total energy for the hydrogen atoms at certain orbit. Okay, in the previous lesson or video, we have discussed the radius of orbit in Bohr's model. So given by R equals to epsilon naught n squared h squared per pi m E squared. Okay, by using the first postulate from Bohr's postulate, and we combine these two using simultaneous equation, we get Rn. So we substitute this Rn into the equation of energy. Okay, so we can cancel out pi. So we get negative me to the power 4. This E squared bring up becomes e to the power 4 per 8 epsilon naught squared n squared h squared. So this is the total energy of the electron in the orbit of the hydrogen atom. Okay, so we separate the 1 per n squared from this equation, me to the power 4 per 8 epsilon naught squared h squared. So n is for orbit 1, 2, 3 and so on. Okay, this equation shows that the electron can only have certain amount of energies depending on which orbit it is in. Because the n here is the integer number, okay, positive integer number. So the energy cannot be in between 1 and 2, in between the level, because this is the in the integer form. So the energy of the electron is said to be quantized. Okay, for n equals to 1, we substitute the values of 1 into here, and the m is mass of the electron, 9.11 times 10 to the power of negative 31, and E is 1.6 times 10 to the power of negative 19. Okay, then to the power of 4, 8 times epsilon naught is 8.85 times 10 to the power of negative 12 squared. Then the H blank Planck constant, 6.63 times 10 to the power of negative 34, to the power of 4 to the power of 2. So we get the answer negative 2.17 times 10 to the power of negative 18 joule. So we convert this to electron volt, okay, divided by 1.6 times 10 to the power of negative 19. So we get negative 13.6 electron volt. Okay, this energy E1 is called the ground state level because the electron usually occupies this level. And by using this 13.6 electron volt, because for the rest of the n, n2, n3, we use the same m e to the power 4 per 8 epsilon naught squared h squared. So we can use this 13.6 electron volt substitute into the equation. So we get negative 13.6 per n squared electron volt. Okay, so the energy of the various stationary state can be calculated from this equation. So for N1, the energy is negative 13.6 electron volt. For N2, so becomes negative 13.6 per 2 squared. So the answer is negative 3.40 electron volt. For N3, negative 13.6 per 3 squared. So we get negative 1.51 electron volt. For N4, negative 13.6 divided by 4 squared. So we get negative 0.85 electron volt. And so on we do for N5, N6, and N7, and we find that the magnitude of the energy is decreasing. Okay, now we are going to plot the energy level graph. So at any instant, the electron in the hydrogen atom can only be orbiting the nucleus in one of these energy levels. So we draw until n equals to 5, because after this is the value become very small, the energy become very small. So the scale here is drawn by 1 unit. Okay, so for n at the ground here, negative 14 volt. So it's negative, so we draw downward, the scale downward. So negative 13.6 will be somewhere here. We draw the straight line to represent the energy level for ground state. For first excited state, okay, between these two scale, so negative 3.40 and so on, negative 1.51. Second excited state, this is first excited state, second excited state, and so on. So this is the equation for hydrogen atoms, energy levels in the hydrogen atoms. For Bose model of the hydrogen atom can also be applied to other atoms with one electron. For example, the singly ionized helium atom, He+, then the doubly ionized lithium atom, Li2+, and the triply ionized beryllium atom, beryllium 3+. So the derivation for En earlier are still valid with one modification. So all E squared term in the formula are replaced with Ze squared, where Z is the atomic number of the single electron atom. Okay, so the equation of the energy becomes negative Z squared me to the power 4 per 8 epsilon naught squared h squared, bracket 1 per n squared, where n start from the ground state 1, 2, 3, and dot dot dot. So Bose model of the atom fails in the case of atoms with more than one electron. So how we get this is we with the same method as the previous slide, but we substitute the Rn equals to n squared h squared epsilon naught per pi m Z epsilon naught epsilon squared. Okay, so we substitute into here. So therefore this Z bring up becomes Z times Z, so Z squared. So that's why we have term Z squared here. Okay, so this energy level drawn here is an example for double ionized atom, lithium atom, L3+, ionized lithium atom L3+, 3+. So the Z value is equals to 3. You can get this from the periodic table. So this is the energy level. So you calculate using this equation. So we draw in the graph here. Okay, that's all for our video. Thank you for watching, and don't forget to subscribe my video if you like it.